So welcome back to image processing class. Today we are going to see what is Wiener filter. In the last lecture we have seen what is inverse filtering and pseudo inverse filtering. So the Wiener filter is the most popular filter used in restoration. The main limitation of inverse filtering and pseudo inverse filtering is they are very sensitive to noise. The Wiener filter exploits the statistical properties of the image and can be used to restore images in the presence of blur as well as noise. So let f of xy, g of xy and f tilde xy. Okay, so what is f of xy? F of xy is the original image, g of xy is a degraded image, and f tilde is a restored image. Okay, there be, so this f of xy, g of xy and f tilde be zero mean random sequences. So what is the meaning of this? Zero mean random sequences. The variation in the gray level within f of xy is, the average of this is 0. Okay, sequences. This is sequences. Okay. So 0 mean sequences imply expectation or average of f of xy is equal to 0. Similarly for g of xy, g of xy is equal to 0 and f tilde also 0. Okay. Similarly, stationary sequences can be defined in terms of correlation. So it is given as f of xy, f of I, comma j. The correlation. This is a correlation. When the signal, the correlation is applied between two same signals, it is known as autocorrelation, right? So this is represented by RFF x minus I, y minus j, and this is for degraded function g of xy, g of I comma j is equal to rgg xi yj. This is autocorrelation. Correlation between the same signals, similar signals. Okay, so we'll give this as number 1. E of f of expectation of this means this is what? This is also a correlation but in different signals. So this is called as cross correlation. X minus I, y minus j. This is known as cross correlation. Okay. So the zero mean image model is given by g of xy equal to hd, where hd is a degradation function, I comma j f of x minus I, y minus j. Okay, let's give this as equation 2, and this will be for I and this will be for j. Okay, So the same thing is represented by f of xy, this block diagram, degradation function hd x comma y. Okay, this you will get g of xy, which is a degraded image, and then we are applying some restoration function hr xy to get f tilde, which is near to f of xy. Okay, so the image restoration involves finding the restored image f tilde x comma y from the degraded image, which is degraded image here g of xy, such that the mean squared error between f of xy and f tilde xy is minimum. That's what I said, right? What I said, this f tilde should be very close to, ideally it should be same as f of xy, but we are achieving practically we will achieve f tilde which is near to f of xy, so the error between f and f tilde should be minimum, right? Yeah, so the mean square image, the mean squared error MSE is given by MSE equal to f of xy minus f tilde xy the whole square, right? This will give equation 3. So MSE equal to, which is given by this, it is for square image, that's why it will be n square. Okay, summation of f of xy minus f tilde xy square, well this is for x is equal to 0 to n minus 1, and this is y equal to 0 to n minus 1. The MSE is minimized if and only if the orthogonal condition is satisfied. If the orthogonal condition is satisfied, that is, the mean square error between f and f tilde is orthogonal to g of xy. Okay, so we'll give this figure as name as figure 1. Okay, so the second part of figure 1 is what g of xy is given to hr xy, that is restoration function, to get f tilde xy, right? Well, H of, what is this? This is what? Restoration filter. So F tilde xy is equal to double summation gi j hr x minus I y minus j. This is equation number 5. Here I will vary from 0 to n minus 1 and j will vary from 0 to n minus 1. Okay. So as stated earlier, f tilde xy should be such that the mean squared error between f xy and f tilde xy is minimum. Okay, so the MSE, the mean squared error, is minimized if and only if the orthogonal property is satisfied, that we already mentioned. Satisfied, right? So what is the meaning of this? The dot product should be 0 for orthogonality, right? So which can be represented as f x minus y minus f tilde x minus y dot gi comma j equal to 0. We now solve this equation. We will get E f x y dot g I j minus f tilde x minus y dot g I j is equal to 0, which can be rewritten as f of xy dot gi comma j minus expectation. This is what? This is now, what is this? Autocorrelation, right? So this is what f tilde xy gi comma j equal to 0. This is 7. So now what we have to do? Now you know what is we have already mentioned what is f tilde. F tilde will get this, f tilde will get it from equation number 5, right? From here we will get f tilde. So that we have to substitute in equation number 7. Okay, so substitute equation 5 in equation 7. We will get E of xy dot gi comma j equal to minus E double summation gi j hr x minus I y minus j g comma j equal to 0. And this will vary from I equal to 0 to n minus 1, j equal to 0 to n minus 1. Which is written as E equal to f of xy dot g of I comma j minus E double summation hr x minus I y minus j into gi comma j into gi comma j equal to 0. This will again vary from I equal to 0 to n minus 1, j equal to 0 to n minus 1. Okay. So that is E f x y dot gi dot j equal minus summation sign. You can bring it out with the restoration function hr x minus I y minus j dot e of g I j dot g I j, which is nothing but what? It's a autocorrelation, right? Equal to 0, 0, j equal to 0, n minus 1, n minus 1. So we'll get E of f of x minus y g I comma j. This will go on that side, so equal to double summation hr x minus I y minus j into e g of I comma j into g of I comma j. Right, again, so I go to 0, j equal to 0, n minus 1, n minus 1. So using equation number 1, now what was the equation number 1? Equation number 1 was this, right? Autocorrelation. So we can use this. Here equation here. You can use it here. So using equation number 1, we get autocorrelation and cross. This is a cross correlation, right? xy equal to double summation hr x minus I y minus j, and this is what? Autocorrelation I comma j. This is autocorrelation, right? And this is cross correlation. So we now take the Fourier transform of the above equation. So after taking a Fourier transform of the above equation, we can write this as S of hg u comma v equal to hr, capital HR, u comma v dot s g g u comma v. Okay, this is equation number 8, where HGGU, V is the power spectrum, it's a power spectral density, and S of FGU, V is the cross spectral density. So using equation number 8, we get what we'll get here. We will get HRU, V equal to SFGU, V upon HGGU, V. Okay, we are just rewriting it. This is equal to what? This will go here. So S of Fg upon SGG, right? Name this as equation number 9. Here equation 8 and equation 9 are called the Wiener filter equations. Okay, so equation 9 gives us the Wiener filter frequency response. The restoration process was explained in equation 5. What was equation 5? Equation 5 was what? F tilde x comma y equal to double summation gi comma j into hr x minus I y minus g, right? I equal to 0, j equal to 0, n minus 1, n minus 1. So this was equation number 5, right? So this is nothing but a convolution operation. So that is can be written as HR x y convolution with g x y. Okay, so computing the Fourier transform, we get capital F u comma v equal to HR u comma v multiplied. Why multiply? Convolution in one domain becomes product in another domain. So g of uv. This is equation number 10. Okay, till now whatever we have seen, in that we have ignored the noise term. Okay, so far we have ignored the noise term. Now let us consider the entire chain. Means now here we are going to consider the degradation as well as the noise. So let us consider the entire chain now as shown in figure 2. Okay, so now f of xy is the original image, then degradation function which is given by hdx comma y. Then there is a noise. Okay, then we'll get g of x comma y. Noise is what? N x comma y, right? So this is given to the restoration function represented by hr x comma y, and then we'll get f tilde x comma y. Okay, so this is restoration and this is degradation. We can show this in a block. Like this, you can show in a block. So now assume that the input signal fx comma y and the stationary noise term which is represented by n x comma y are uncorrelated. The degradation part is given by g of xy equal to f of xy convolution with hdxy, that is degradation function, plus noise x comma y, that is g of x comma y equal to summation, double summation of hd x minus I y minus j f I j plus n x comma y. Okay, where I will vary from 0 to n minus 1, j will vary from 0 to n minus 1. Okay, since fxy and nxy are uncorrelated, nxy is orthogonal to fx comma y, that is this condition is true. fxy dot nxy equal to 0 for xy I and j. Okay, so this gives us sgg u comma v equal to mod of x u comma v square sff u comma v plus snn u comma v. And sfg u comma v equal to h complex conjugate u comma v sff u comma v. Since we know hr uv equal to sfg u comma v upon sgg u comma v, we get hr u comma v equal to, what is sfg? You have to substitute this here, so you will get h complex conjugate u comma v to sff u comma v upon what is hgg? Hgg you can take it from here, This you have to substitute here. So you will get HUV square SFFUV plus SNNUV. This is equation 11. Here SFFUV and SNNUV are the power spectra of the signal and noise respectively. So this is the Wiener filter. Okay, so we notice that the filter is completely determined by the power spectra of the signal. And the noise and the frequency response of the imaging systems. So HR U comma V is given by H complex conjugate U comma V upon mod of H U comma V square plus SNN U comma V upon SFF U comma V. This is equation number 12. Yeah. So the Wiener filter, is real and even. From figure 2, in figure 2 we have shown degradation as well as the noise, right? From figure 2 it is evident that the image gets degraded due to the degradation, like for example blurring. Okay, blurring function and the additive noise component. Effect of the two, we will see the effect of these two separately. So suppose for example, first is suppose no blur and only additive noise. Okay, so H of U comma V will be equal to 1, and which is shown by f of xy h equal to 1 noise, and you will get g of xy. So from equation 11, what was equation number 11 here? Sorry. This equation number 11. Okay, we have to substitute h here. Okay, so from equation 11 what we'll get? From equation equation 11 we get HR u comma v equal to SFF u comma v upon SFF u comma v plus SNM u comma v. So which can be written as SFF u comma v upon SNM u comma v divided by 1 plus SFF u comma v upon SNN u comma v. Now SFF u comma v upon SNN u comma v is signal to noise ratio SNR at frequency u comma v, right? So HR u comma v at HU comma v equal to 1 will be equal to SNR upon 1 plus SNR. So from the equation we realize that when the signal to noise ratio is large, what will happen to HR? HRUV will be almost equal to 1, and when SNR is small, HR will be equal to HRUV will be equal to SNR, right? Hence HR u comma v acts as a low pass filter. It is also known as the Wiener smoothing filter. Okay. Second case we'll see no noise but only blur is there. Okay, so only blur is there, noise component is not there. So since the noise term is absent, SNN will be equal to 0. So equation 11 will reduce to equal to SNN equal to 0. We will get H complex conjugate U comma V upon H of U V. Okay, so that can be rewritten as, that is HR U comma V SNN equal to 0 can be written as 1 upon HUV, right? This is nothing but what? This is nothing but the inverse filter which we have already seen. Since blurring is usually a low pass operation. The Wiener filter in the absence of noise acts as high pass filter. So what is the interpretation of this case 1 and case 2? In case 1 we said that there is, what we said, there is no blur but there is only additive noise, and in case 2 we said that there is no noise but only blur. So what is the interpretation of this case 1 and case 2? In the presence of only noise, the Wiener filter acts as a low pass filter, while in the presence of only blur, the Wiener filter acts as a high pass filter. When both noise and blur are present, the Wiener filter achieves a compromise between a low pass and high pass filter, resulting in a band pass filter.